Hello, I'm here with a brief lecture on section 2.2, separable ordinary differential equations. We're going to identify separable ODEs. We're going to solve a couple of separable ODEs given two examples. So first, our definition: a differential equation is separable if it can be written in the form derivative of y with respect to x is equal to a function of x times a function of y. So if you solve for the derivative, get the derivative on one side of the equation by itself, and then on the other side of the equation, if you can separate those functions into a function of x times a function of y, then you have a separable ODE. Notice that something like dy over dx equals x plus y is not separable because x plus y cannot be factored into a function of x times a function of y. So this is not separable. But we'll look at two examples today on separable equations. So basically, to solve, you separate the variables and then integrate both sides. The method is separate the variables so that you have all y terms, including the differential of y on one side, and you have all x terms, your function of x, and the d of x on the other side of the equation, and then integrate both sides of the equation. When you integrate, you actually get a constant on both sides, and we'll combine those two constants into a single constant. So generally, we don't add that constant on the side that contains the dependent variable y. We'll just include it on the side that contains the independent variable x and just call it c. If at all possible, solve for y. Sometimes it is not possible. And then if you're given an initial condition or a boundary condition, plug it in and solve for c to get the particular solution to the equation. So here's our first example. It's a nice simple example. We have the derivative of y with respect to x is equal to x times y. Notice that we have a function of x times a function of y. We could take this equation, and I'm going to start by multiplying both sides by dx. That gives my x terms over to the right side. And I'm going to divide both sides by y. So my dx's will cancel on the left side. My y's will cancel on the right side. And it gives me dy over y equals x dx. So we separated the variables, and now we'll integrate both sides. When you integrate dy over y, we get the natural log of y. Remember that the constant of integration, we're just going to use it on the right side. When you integrate x, we're going to get x squared over 2 and then plus c. So if at all possible, we want to solve for y. To solve for y, we can apply the exponential to both sides of the equation. And then the e and the natural log will cancel to give me y. On the right side, I'm going to write this as e to the x squared over 2 times e to the c. Remember that your rules of exponents are that if you have a base like a raised to the x plus y power, you can write that as a to the x times a to the y. In this case, that x squared over 2 plus c is all the exponent. And so you can break that up. I don't like my constant being e to the c. So off to the side, I'll say let k equal e to the c. And then we get y equals k e to the x squared over 2 as our general solution to the equation. So the general solution is a solution that contains the constant of integration. In this case, our k, and it gives us a family of solutions where k can be any real number. And the second example we're going to look at is an initial value problem. An initial value problem is an equation where you're given an initial value, y of 0, which allows you to solve for the constant of integration. So here's my differential equation. I have my derivative isolated already on the left side. On the right side of the equation, I notice that I have an x in common that I can factor out. So this will give me dy over dx equals x times y squared minus 1. And there's my function of x times my function of y. It's my f of x equals x. My function of y, g of y, is y squared minus 1. We can separate the variables by multiplying both sides by dx. That'll cancel the dx on the left side. And it tells me my x terms go on the right side. And I'm going to divide by y squared minus 1. This gives me, I'm going to write that as 1 over y squared minus 1 dy is equal to x dx. So all the y terms are on the left side of the equation. All of the x terms are on the right side of the equation. We can solve by integrating both sides of the equation. And then on the left side, I have this integral 1 over y squared minus 1. Off to the side, I'm going to do partial fraction decomposition. You should have done this in your calculus class. I know that y squared minus 1 is y minus 1 times y plus 1. And so I can break up this fraction into the sum of two fractions, a over y minus 1 plus b over y plus 1. And then multiplying through by the common denominator, I get 1 is equal to a times y plus 1, and then plus b times y minus 1. I'll simplify the right side of the equation by distributing through by the a and then distributing through by the b. We get ay plus a plus by minus b. And then I'll combine my like terms. My y terms are like terms. I'm going to factor out the y. And then my constant terms are like terms. So here, I want to write the left side of the equation as 0y plus 1, so that I have my y terms and I have my constant terms. And I want to equate the coefficients. For the y terms, I have a plus b equals 0. Those coefficients should match up. A plus b equals 0. And for my constants, I have a minus b is equal to 1. That gives me a system of equations that I can solve. I'm going to solve these by adding, because I see that when I add, the b terms cancel out. It'll give me 2a equals 1, divide by 2, and we get a equals 1/2. And then because a plus b is 0, I know that b has to be negative 1/2. So a is 1/2, b is negative 1/2. I'm going to substitute those in for a and b and rewrite my integral on the left side of the page as, let's see, a is 1/2. So I've got 1/2 times 1 over y minus 1. B is negative 1/2 minus 1/2 times 1 over y plus 1. And I'm integrating that with respect to y. On the right side, I'm integrating x with respect to x. And now I can work this through. The 1/2 and negative 1/2 are just constants. That carries along 1/2. When I integrate 1 over y minus 1 with respect to y, I get natural log of y minus 1. And then minus 1/2, the integral of 1 over y plus 1 is natural log of y plus 1. On the right side, when you integrate x, you get x squared over 2, and then plus c. So I notice I have a 1/2 in common in almost every term. And so I'll multiply both sides of the equation by 2. To get rid of that 1/2, it's going to give me natural log of y minus 1 minus natural log of y plus 1 equals x squared plus 2c. I can use my rules of logs to combine that difference of two logs together into a single log. The log of y minus 1 over y plus 1 equals x squared plus 2c. And I want to solve for y if at all possible. And so I'll get rid of that natural log by applying the exponential to both sides. And I'll go to my next page. I get y minus 1 over y plus 1 equals e to the x squared times e to the 2c. And here again, I'm going to make a substitution. I'll let k equal e to the 2c. So I get y minus 1 over y plus 1 equals k e to the x squared. Now, to solve for y, I need to get that y plus 1 out of the denominator. Multiply both sides by y plus 1. On the left side, the y plus 1s will cancel. On the right side, I'm going to distribute. I'll get k y e to the x squared plus k e to the x squared. And to get my y terms together on the left side of the equation, I'm going to subtract ky e to the x squared from both sides. And also add 1 to both sides. So the 1s will cancel from the left side. That ky e to the x squared cancels from the right side. I get y minus ky e to the x squared equals k e to the x squared plus 1. And we're almost done. On the left side, we could factor out that y to get 1 minus k e to the x squared. And then divide. Divide by 1 minus k e to the x squared. And we have our general solution. Y is equal to k e to the x squared plus 1 over 1 minus k e to the x squared. That's our general solution. The general solution is the solution that contains the constant of integration, or that unknown value of k. I'm going to copy my general solution. Copy it. I'll bring it up here to the top of the page. And then go back to our problem and grab the initial condition. Y of 0 equals 2. And substitute in to solve for k. So let's see, y is 2 when x is 0. So e to the 0 is 1. Those exponentials will drop out. It'll give me 2 equals k plus 1 over 1 minus k. I'm going to think of 2 as a fraction so that I have a proportion, and I'll just take cross products. Multiplying 2 times 1 minus k, we get 2 minus 2k. Multiplying 1 times k plus 1 gives me k plus 1. I'm going to add 2k to both sides and subtract 1 from both sides to get 1 equals 3k, and then divide by 3, and we get k is 1/3. So k is 1/3. If I take my general solution and put 1/3 in place of k, I'll get 1/3 e to the x squared plus 1 over 1 minus 1/3 e to the x squared. And because I don't like fractions within fractions, I'm going to multiply by 3 over 3. And then that 3 will distribute to each term in the numerator and in the denominator to give me my final solution. 1/3 times 3 is 1, so that first term becomes just e to the x squared plus 1 times 3 is 3. In the denominator, 1 times 3 is 3, and for the second term, 1/3 times 3 is 1. And this is it's called the particular solution. Or the solution that corresponds to the initial value problem. And that finishes the brief lecture for 2.2.